Hi, this is Barrett Givens, and in this video, I want to show that homeomorphism is an equivalence relation. Homeomorphism is an equivalence relation. So uh, it's kind of, you kind of might guess that this was true based on the notation that we used, right? For homeomorphic, different books use different notations, but for homeomorphic, they tend to use notations like an equal sign with a squiggle, or like a congruent sign with like the three equals, or maybe just like a single line with a squiggle or just a squiggle. But these are the kinds of symbols that mathematicians use when they're talking about something which is an equivalence relation. And remember that being an equivalence relation means you kind of act like equality, okay? It's like some way of saying that things are really sort of the same as each other in some sort of way. All right. And we've already talked about the definition of an equivalence relation. If I say that homeomorphism is an equivalence relation, what that means is I'm saying that these three properties hold. First of all, that it's reflexive, that any topological space is homeomorphic to itself, okay? Secondly, that it's symmetric, that if X is homeomorphic to Y, then Y is homeomorphic to X. And then third is that it's transitive. If X is homeomorphic to Y and Y is homeomorphic to Z, then X is homeomorphic to Z. And so if we're using a symbol that looks like an equality sign, then we would want it to satisfy these three properties. If it didn't, then we probably shouldn't be using that symbol for it. Okay? So let's go ahead and show that homeomorphism is an equivalence relation by showing that it satisfies these three things. And remember that being homeomorphic means that there exists a homeomorphism, which means that there exists a function from the one space to the second space, which is one-to-one onto continuous and has continuous inverse. So first, let's talk about being reflexive. Let's talk about being reflexive. So for being reflexive, I have to find a function that goes from a space to itself. And I don't know anything about what this space is, but it has to go from the space to itself, and it has to be one-to-one onto continuous and have continuous inverse. Well, there could be more than one possible way to do this, but the one way that works no matter what the space is I'm just going to let my function be the identity function x. So then f goes from a space to itself. We've seen previously that no matter what your topological space is, this function is always continuous. Okay, so this is a continuous function. It's clearly one-to-one and onto. It's clearly a bijection. And its inverse is also itself. And so this is a homeomorphism. And so we are done. F is a homeomorphism. All right. So to show homeomorphic, we have to give an example. All right. Now let's talk about the symmetric property. So here we're proving that if X is homeomorphic to Y, then Y is homeomorphic to X. So let's assume that X is homeomorphic to Y. That means that there's at least one function, a homeomorphism, F from X to Y. So because it's a homeomorphism, that means it's one-to-one, it's onto, which means its inverse exists, and F is continuous, and also F inverse is continuous. So how can I'm trying to prove that Y is homeomorphic to X, so how can I get a function that goes the opposite direction? Well, we already mentioned it just now. We'll let G be F inverse. Then G goes from Y to X. And because F is continuous, that means G inverse is continuous. And because F inverse is continuous, that means G is continuous. So G is continuous, G has continuous inverse. It's the inverse of a bijection, so it is also a bijection, and so G is a homeomorphism. Which implies that Y is homeomorphic to X. Okay? So if we have a homeomorphism that goes one direction, then its inverse goes the other direction and is also a homeomorphism. Okay? Well, sort of what we just proved is that the inverse of a homeomorphism is also a homeomorphism. All right, and then the last one is the transitive property. So let's assume x is homeomorphic to y and y is homeomorphic to z. That means I have functions f from x to y and g from y to z. And I'm trying to prove that x is homeomorphic to z. I want to prove that x is homeomorphic to z, so I need to find a function that goes from x to z. Okay? And we've also seen this before. If f goes from x to y and g goes from y to z, how do I find a third function that just goes directly from x to z? Yeah, I'll take the composition. Let h be the composition G circle F, G composed with F, then H goes from X to Z. And is H a homeomorphism? Well, F and G are both continuous, and we know that composition of continuous functions is continuous, so H is continuous. What about H inverse? H inverse, using properties from abstract algebra or just properties that you might have learned in other classes, H inverse is F inverse composed with G inverse. Since F and G are homeomorphisms, F inverse and G inverse are continuous. So H inverse is a composition of continuous functions, which means H inverse is continuous. So H is continuous. H inverse exists and is continuous. That means that H has to be a bijection. And so H is a homeomorphism. H is a homeomorphism, which implies that X is homeomorphic to Z. Okay, H is homeomorphic to Z. So if you have a function from X to Y and another function from Y to Z that are both homeomorphisms, then their composition is a homeomorphism from X to Z, and so we get the transitive property. All right, so being homeomorphic is an equivalence relation. And so you can really think of it as saying that if X is homeomorphic to Y, then topologically it's like they're the same, okay? They're the same space, just maybe with a different label or a different way of representing it. But in all the ways that matter to us as topologists, they're going to end up being the same spaces. One last piece of information for this video is that we have another piece of terminology which can sometimes help a little bit in just explaining what we're doing, which is that if you have a function f from x to y, if f of u is open in y whenever u is open in x, we call f an open map. So this is really similar to the definition of continuous. F is continuous if the pre-image of open sets is open, and it's open if the image of open sets is open. And so being an open map is the same thing as saying that F inverse is continuous. And so we can say that F is a homeomorphism. F is a homeomorphism if and only if F is one-to-one, onto, continuous, and open. Okay? Because being open is the same thing as saying that F inverse is continuous. All right. Thank you for listening.